Principle of mathematical induction. To understand this, first we need to know what is a statement. A sentence which may be true or false is called statement. For example, we can say that 5 is greater than 3. And also we can say that 5 divides 13. We know that the first statement is true, whereas the second statement is false. But both are statements. The statements which involve mathematical relations are called mathematical statements. Now we need to know why principle of mathematical induction is used. So whenever we find it difficult to prove a statement or a theorem by direct method, we use this indirect method, which is known as the principle of mathematical induction. It contains a special technique of proving a statement or theorem for all positive integers in just 2 steps. So what are those? Step 1. We need to verify that the given statement is true for 1 or 2 particular values of n. Let's say n equals to 1 and 2. So this is the first step. Now let's see what the second step is. For the second one, we assume that the statement is true for n equals to m, where m is any positive integer. Then we'll show that it is true for n equals to m plus 1. This principle of mathematical induction, how do we find it out? Now, if P of n be a statement such that number 1, P of 1 is true, and number 2, P of m plus 1 is true whenever P of m is true, where m is any positive integer, then P of n is true for all positive integers n. To understand this better, we need to look at some examples. So we'll start with a simple one. The first example is that if n be a positive integer, show that n into n plus 1 is an even positive integer. Now what is the solution? Here statements are very important. So we'll start this. Let Pn be the statement, which is n into n plus 1 is an even positive integer. So first we'll need to prove number 1 step. P of 1 is the statement 1 into 1 plus 1 equals to 2. We know that this is an even positive integer. Therefore, P of 1 is true. Now heading on to the second one. If P of m is true for some positive integers m, then m into m plus 1 is an even positive integer. Now we substitute wherever there was m with m plus 1. So we will get m plus 1 into m plus 1 plus 1. This gives us m plus 1 whole square plus m plus 1, which can be simplified into m square plus 2m plus 1 plus m plus 1. This can be written as m square plus m plus 2m plus 2. Taking common, we write m into m plus 1 plus 2 into m plus 1. We know that this is true because we have assumed that P of m is true. Also, 2 into m plus 1 is obviously true, is obviously an even positive integer. Hence, adding them we get an even positive integer. Therefore, P of m plus 1 is true when P of m is true. So, by the principle of mathematical induction, P of n is true for all positive integers Hence, we can write that n into n plus 1 is an even positive integer. Now heading on to the second example, which is an even simpler one. Using principle of mathematical induction, we need to prove that the statement is true for all n belongs to natural numbers. The statement is 1 square plus 2 square plus 3 square till n square equals to n into n plus 1 into 2n plus 1 by 6. We already know that this is true, but we need to prove this using the principle of induction. Now we are going to follow the same procedure, which is let Pn be the statement which is 1 square plus 2 square plus 3 square plus till n square equals to n into n plus 1 into 2n plus 1 by 6. First, we need to check for n equals to 1. The LHS gives us 1 square, which is 1, and the RHS gives us 1 into 1 plus 1 into 2 into 1 plus 1 by 6. This gives us 1 into 2 into 3 by 6, which equals to 1. Hence, LHS equals to RHS. This means that P of 1 is true. Now assuming that P of M is true, where M belongs to natural numbers, then P of M is the statement 1 square plus 2 square plus 3 square till m square equals to m into m plus 1 into 2m plus 1 by 6. Now we add m plus 1 whole square to both the sides. From this we get 1 square plus 2 square plus 3 square plus till m square plus m plus 1 whole square, and on the right hand side m into m plus 1 into 2m plus 1 by 6 plus m plus 1 whole square. This equals to, we take m plus 1 is common, and this gives us m into 2m plus 1 by 6 plus m plus 1. This equals to m plus 1 into 2m square plus m plus 6m plus 6 by 6, and this equals to m plus 1 into 2m square plus 7m plus 6 by 6, which equals to m plus 1 into 2m square plus 4m plus 3m plus 6 by 6. From this we can take common, which is m plus 1 into, taking 2m as common, we get m plus 2, and again taking 3 as common, we get m plus 2. So from here we can write m plus 1 into m plus 2 into 2m plus 3 by 6, and this can be written as m plus 1 into m plus 1 plus 1 and 2 into m plus 1 plus 1 by 6. So this is in the form of our given statement, which means that therefore P of m plus 1 is true when P of m is true, Therefore, by the principle of mathematical induction, P of n is true for all n belongs to natural numbers, and hence 1 square plus 2 square plus 3 square plus till n square equals to n into n plus 1 into 2n plus 1 by 6. In mathematics, we cannot ever let trigonometry lag behind. So this third example, we need to prove using the principle of mathematical induction this statement, which is cos alpha into cos 2 alpha into cos 2 square alpha till cos 2 to the power n minus 1 alpha equals to sin 2 to the power n alpha by 2 to the power n sin alpha, where n belongs to natural numbers. By following the same procedure, we write that let P of n be the given statement. Which is cos alpha into cos 2 alpha into cos 2 square alpha till cos 2 to the power n minus 1 alpha equals to sin 2 to the power n alpha by 2 to the power n sin alpha. First, we need to check for n equals to 1. From here, we know that LHS gives us cos alpha and RHS gives us sin 2 alpha by 2 sin alpha, which equals to, now expanding this we get 2 sin alpha cos alpha by 2 sin alpha. From this we can write it equals to cos alpha. Therefore, LHS equals to RHS, and hence P of 1 is true. Now the second step is assuming P of m is true. Then the statement becomes cos alpha into cos 2 alpha into cos 2 square alpha till cos 2 to the power m minus 1 alpha equals to sin 2 to the power m alpha by 2 to the power m sin alpha. Now for P of m plus 1, we need to multiply both the sides by cos 2 to the power m alpha. From that we get cos alpha into cos 2 alpha into cos 2 square alpha till cos 2 to the power m minus 1 alpha into cos 2 to the power m alpha, which equals to sin 2 to the power m alpha into cos 2 to the power m alpha by 2 to the power m sin alpha. Now this equals to 2 into sin 2 to the power m alpha cos 2 to the power m alpha by 2 into 2 to the power m sin alpha, and this gives us sin 2 into 2 to the power m alpha by 2 to the power m plus 1 sin alpha, which equals to sin 2 to the power m plus 1 alpha by 2 to the power m plus 1 sin alpha. Thus, P of m plus 1 is true when P of m is true. Hence, by the principle of mathematical induction, P of n is true for all n belongs to natural numbers.